three-state contention. Let me just take a pen or I'll show you what is three-state is better. This is buffer. We'll see that again. Okay, we'll discuss on this. But from this, in real time, the issues will be quite different. Anyway, what is this? So, eh, tri-state, tri-state bus convention is something where it has three states. Tri means three. So bidirectional. It's bidirectional is a the we have two states. Okay. So there will be different scenarios in real time. These are types of buffers. Okay. Bidirectional and tri-state. So tri-state is something where this buffer has an enable signal. Apart from the input and output, it has a enable signal. When enable is high, then only the input value will be propagated to the outside. So this kind of scenario where you have two tri-state buses driving a common point. Okay, so this value is captured from two different tri-state buses. Okay, so that means this is an AND gate. Assume this is an AND gate. Okay, AND gate input is coming from some combination logic, and again this is coming from another combination logic. Okay, so this combination logic output is driven by some logic and control, and this is also driven by some logic, or both of them. Okay, there will be another scenario where both are tied to a common cell. So it might come from this. Sorry. Okay, so one scenario is where you have this kind of environment. You don't know what is a input driver for this logic and this logic, but we are getting the value. Now, as long as you are getting some random value, it is fine. Okay, and this particular AND gate is a processing element, so it will take input and it will process. Okay, let's say that if this is not the case. Okay, If this is not the case, see, this scenario is correct, guys. You are getting some input from some combination logic, another input is coming from another combination logic. This scenario is fine. But when you have a flop rather than a gate, or the same gate, these both are driving to one point. Okay. And this is your D input. If this is the scenario, tool will not understand which one to take it. This is a contention issue. Bus contention issue. This is called bus contention issue. Okay. When tool is not able to take which one to be taken, which data to be taken first, because both are driving same to the same point. Okay. So the driving scenario might change. The driving scenario might be like from the same common point you are getting this kind of source, or if this particular logic is not there, let's say this particular logic is not there. Okay. And only you have this kind of scenario. In this scenario, if you have a tri-state bus, okay, and you have a enable signal, you also have the same here. So this is a controlling element. I mean, this buffer has a control element which has to be enabled again. Same here. If it has a tri-state buffer, okay, and it has a control signal, when you enable that control of the buffer, then only the value can pass through. So if you have this tri-state buffer issue, then this is a tri-state buffer contention issue. So the issue is the same contention. Contention is the same. The scenario of contention and the meaning of contention is same. It will not change. The driving element might change. Contention might be caused by any of the scenarios. End of the thing is that it is driving to the same common point. Okay. So both of these are driving one common point. Same here. Okay. This bidirectional is also similar to your tri-state, but this what we call uh, this enable is common for both of this, and the connectivity of bidirectional is something like this. Okay, this input is fed back to this, and you will give input here and you will collect output here. So even this logic is not accepted or understood by the tool. So tool will throw error of a bidirectional issue. So this is a type of um, bidirectional tri-state. We stopped writing in RTL code. We no longer write in RTL code now with this tri-state bus. Even if we are writing, we are writing it in a separate module, which is not part of your scan logic. Okay. So this is no longer we have. So majority of the times you will not have these issues. Majority of the times. Okay. Because contention is a big issue for verification, guys. Yeah. So bus contention is a big issue for verification. The design verification engineers, they have to perform simulations, the validation. Okay, so verification is something that you provide stimulus and capture the response. So when you're trying to provide stimulus through these two inputs, and you want to capture output of this flop, then tool will have a contention issue where tool will not be able to identify which input to take. Okay, in in real time, even if bus contentions are accepted, I mean this bus contention will not cause any issue that will what we say, um, that is a problem for our scan, for the current scan rolls. We can fix this with the timing, with the delay. So first this particular, if you want to enable this particular data first, you will have a delay on this particular cell. So likewise, we will add delays in real time. So at a time, both will not be driven. And clock feeding multiple register inputs. So this part is understood. Tri-state contention issue is understood, right?
Yes, sir.
Yes, sir.
So tool also gives the ability whether to enable contention check. Okay, let's say RTL has a contention, bus contention by default. RTL code is written with contention. Lot of bus contention in the sense tri-state buses and buffers. So when you have a lot of tri-state buses and buffers, obviously you will end up with contention. So are you going to check contention part of your DFT scan design rules or not? There is a command to enable that. So if you disable that, most of the time we disable it because we are not concentrating on tri-state, because tri-state might be a necessity as per the functional logic to uh, create modules and functional blocks. Okay, writing the functional blocks. Sometimes we need tri-state buffers. So that is a needed functionality. As per functionality, if it is needed, you will have it obviously in the design, and whether you want to check it or not is up to you. So what happens if you check it? If you check it, you will end up with contention issues. You cannot proceed further. If you don't check it and ignore, there is no problem, because there is no escape for that. The tool will not be able to understand contention, and tool cannot proceed with contention if you enable contention checks. Okay, so and this contention is not a biggest problem when we are not dealing with the DFT. Particularly DFT people are not dealing with any of these contention issues. It is a functional validation issue. Functional team has to modify it as per the functional validation team response. DFT has nothing to do with this. So in DFT, you can just ignore this. Okay. Trusted buses are a functional bugs. If you feel it as a bug. Okay. That's the knowledge behind this trusted bus. Next, clock feeding multiple register inputs. So a clock that feeds multiple register input reduces the fault coverage attainable by ATPG. The signal can be one of the following: a clock signal that feeds into more than one register clock pin, a clock signal that feeds into a clock pin, and an asynchronous control of a resistor. So let's see the images, we'll understand. So clock is going to some combination logic, and the combination logic, uh, one of the input might coming from reset. So indirectly, this clock is going to clock pin as well as a reset, because what are the combination logic that we have, it is both indirectly feeding it to the reset. So in this kind of scenario, tool will throw an error D12, and this D12 DRC has to be fixed. Okay, so this clock C connects to clock set or reset inputs. This will indirectly toggle the reset if clock is connected to reset. Okay, whenever clock is high, whenever the clock is high, reset also will get high. So this has to be broken we will break this issue. And so far, I'm trying to explain all the DRCs that we have, how the design rule checks are categorized. Next session, we will, I mean, within the same session today, we will try to discuss on the DRC debug. For each and every DRC, what is the solution, how to debug, that we will discuss. Okay. So this particular thing, clock signals feeds register clock pin and asynchronous reset. So this scenario is very bad. You have to break this. You have to make sure that if functionally this is wrong as well. Okay. As functionality wise also, this should not happen. So these are regular way of generalizing the DRCs. By default, DRCs are categorized and given to the tool. So we are just learning what are the type of DRCs. In real time, you might face or don't face this issue depending on the RTL engineer, how he writes the code. Okay. So if a matured engineer or a what we call a study stable engineer will write a good RTL code, so you will not face these issues. And this particular RTL manager will take care of that particular team properly, train them accordingly to provide a perfect RTL code. Okay, so in olden days we used to have this big issues where DFT team or physical design team used to get back to front end team, the RTL team, always telling that these are the functional issues we are facing. This particular logic connection is wrong. Like this, we used to continuously mail them by taking a screenshot of the image or the schematic. But day by day, I mean, for today's scenario, I'm telling, we don't see this kind of junk issues anymore. Okay, because the tools are much more efficient now, and the even RTL coding, even if RTL engineer is not writing the code properly, the RTL engine, the tool, uh, throws an error or warnings stating that these are the DRCs that you have in the written code. So it's obvious now. Okay. And few teams in real time, they RTL manager says run Spyglass after RTL design to know the existing DRCs before delivering it to physical design or a DFT team. So that is saving a lot of time actually. So even few companies do that. Okay. In Intel Bangalore, I think pretty much it's a Spyglass flow. People use Spyglass at RTL stage, and they identify any kind of design bugs, and they give it to DFT team for further DRC debug and synthesis. So this part, till this part, it is understood.
Yes, sir.
Okay. So violations that reduce fault coverage. There are certain violations that reduce fault coverage, but this will not impact uh, the flops to be converted to the scan. So what is that violation that reduce fault coverage? Combinational feedback loops. These are very serious issues. Nowadays, we don't see it in real time. Very less. Okay. But depending on the company to company and RTL engineer, how he writes. Clocks that interact with register input. That means clocks are indirectly driving the register data input or the D input of that particular register flip flop. Multiple clocks that feed into latches and flip flops. Black boxes. Okay, so let's see for one by one. Combinational feedback loops. So what is a feedback loop? This feedback loop, I'm sure that you have learned in your academics about the feedback loop in your digital design. it is the same concept. So we'll see the diagrams. What is that combination loop? Okay. So this particular U1 input is an output of this particular the same driving fan out cone. So the same fan out cone output is feeding as input again to the one of the driving element. Then this is the biggest feedback loop issue you'll see. And these are what we say for these also we have two scenarios in DFT. Either we identify feedback loops or don't identify them. If you identify them, okay, then you have to fix it mandatorily. This is this is a big issue. This will end up uh, the tool will continuously be in loop if you run with this circuit. The run with the, I mean, so there is a concept called write a script, run the script. In run the script, when you run the script, tool is invoked. That means tool will start. Tool will start executing the script. If your design has any loop, feedback loops, your tool will hang. Because in practicality, tool will hang in the sense tool will continuously stay in that loop because it is performing some activity, right? It is trying to test it. Okay, these tools are problematic for ATPG, not for scan insertion. These are, as I mentioned, this is related to coverage. Fault coverage, test coverage, all are these elements come into picture during ATPG, test pattern generation. After you do scan insertion, compression, then you do pattern generation, right? So in that pattern generation, fault coverage is very important, and we have test coverage concept. So these two concepts will come into picture, and this kind of pre-DFT DRCs that we ignored are set into warnings, not errors. So all these warnings will be will cause lot of issues during pattern generation, which will reduce your fault coverage. So a tool might hang because tool will try to the circuit we have already have, right? So tool will try to create pattern to test this logic, right? So tool has to place some value here and here. So can the tool place a value here? Is there a possibility to place a value here for the tool?
No, sir.
Now it is dependent on this input and this input, right? So if you don't, tool doesn't have controllability on this particular input, it has to depend on this input only. So this is what NOR gate, right? These two are NOR gates. So NOR gate, the behavior of NOR gate is if either of, I mean, both the inputs are 0, okay, the output is high. If either one input is high, okay, then the output is 0. That is the behavior of NOR gate, correct? Now, let's take the combinations. Let's say one input, this input is 0, okay. Do you require other input also to practically get a proper output value? Yes. For NOR gate, if one input is 0, you definitely need other input value also to estimate the output value, right? So other output might be 0 or 1, right? If this one input is high, 1. So based on the NOR behavior, irrespective of other input, the output is 0 because input is high. One input is high. Correct? This scenario is understood.
Yes, sir.
If one input of the NOR gate becomes 0, then you definitely need the other input value. So in that scenario, tool will not be able to test this particular path. So when your tool is not able to test this particular path, the faults on this particular line, how many faults you will have? Two faults on every line. Zero, stuck at 0, stuck at 1. So these two faults are not identified. So like these scenarios, how many scenarios we have? Feedback loops in our design. All that fault coverage will be lost. Out of 100%, if you take in this particular small circuit, you lost 40% coverage. Okay. So this kind of issues has to be resolved or taken to the RTL team, stating that there are feedback loops. Are you going to fix it? Is this functionally correct? Do you need this feedback loop as per the functionality? If yes, we cannot do anything. And we need a coverage. Then we have to break this. And for DFT purpose, we have to break this and create a mux with a uh, bypassing this and creating random value. Okay, known value. So tool can also fix it nowadays. Tool has the feasibility to fix the feedback loops, but manually, if you want to, an engineer has knowledge on how to break this feedback loop, then you can do it. So this is an OR gate behavior. So irrespective of input value, and you want to give a solid uh, zero value or a zero value or a one value, fixed value to this one input, then you can what we call, you can at least cover few faults. Okay. So in this stage, uh, this particular nor other input, if you fix to 0, okay, what are the faults you can cover? Here 0 and 1 will be fixed. Here the behavior of in this particular line, one 0 fault is fixed. I mean, you are um, targeting the 0 fault already by giving 0, forcing the value to 0. And one more thing that we can do is, instead of 0, make it 1. So if you make it 1, you are testing only the one fault. 0 cannot be tested. So either of this scenario can be tested in this. Okay. So you are trying to bring little bit of coverage by breaking this particular loop. Okay. So this you can do based on the RTL input. So if RTL engineer says that this is functionally required, and try to add DFT logic to break this loop for DFT purpose, then we will break it and we will do manual fix. That is where the DFT expertise comes in. So for fresher, we will not do this. Senior engineer will, or your lead or somebody like me, will try to fix this issue for you when you have this issue. So you have to bring this issue in real time when you face this. But interviewer will not expect that answer. Okay. But you can say that how to fix this, you break the loop by adding extra logic to make sure that at least one or the other fault is covered here. Okay. Any queries here?
No, sir.
Okay. So we will discuss the how to debug feedback loops also. All these DRCs we'll discuss in another next few minutes. Okay. Once let the all the DRCs uh, be understood, then we will find solution how to debug each DRC. We'll discuss that. I have a separate presentation for that. So next thing is clocks that interact with register input like this. Clock is going to some combination logic, and combination logic output is directly driving to the D input. So this scenario, I think previously also we have seen. the D9. So D9, D10, some again the similar DRCs. So if this kind of scenario, that is D10. We have D9 DRC previously seen. So all these DRCs has to be fixed, and these are not correct as per DFT. Okay, so we have to inform this kind of scenario to any kind of DRC that is functionally you are feeling that okay, functionally this shouldn't be here. Then you have to give it to the RTL team so that they will redesign and make sure this clock is not directly feeding to the D input of the problem. Okay, is it clear? Okay.
Yes, sir.
Next, multiple clocks that feed into latches and flip-flops. The following types describe the types of clock getting functions. Okay. Latch requires multiple clocks to capture data. Mhm. So this is D8. D8. Basically, D8 is a different DRC, right? Uh, Clock cannot capture data. This is an adequacy issue. Hmm. Usually, you will not see this kind of DRCs for D8. Mm, you will see something different, but this kind of clock gating cells we don't encourage. We maintain synchronicity across entire design to maintain a common standard cell. Okay. As last time I told you guys, we read in standard cells, right? So your entire SOC design will be using the same kind of standard cells. Standard cells means the standard cell libraries of AND gate, OR gate, NOR gate, clock gating cells, flip flops, registers, muxes. All these is individual modules or elements that we have. For all of that, we will read a common style. So RTL design engineer also has to use the same standard cells. Whatever RTL design engineer uses, we use the same. Okay. So in order for the DFT friendly, okay, see remember each and every sentence that I'm trying to say, because these sentences you have to try to use these sentences in your interviews when they ask this kind of tricky questions. Okay, so you should give a proper response. If somebody asks you this kind of violation, clock cannot capture data with other clocks of like D8 violation, then you have to say that this kind of scenario in real time we will not face it. Okay, this is not a good example of a clock gating cell. Will not. So what you see here is a D1 clock, D2 clock 2 going to two AND gates followed by an OR gate followed by, assuming this is a latch. I think that is what he is telling that this is a latch or a flip flop. Otherwise, this kind of clock gating element, two AND gates with OR gate. Okay, so with if you are considering a single clock gating cell in this scenario, it cannot have two different clocks. Either it should be a same clock. Okay, with two different clocks, tool cannot process. Indirectly, what is happening is one clock is going to A, finally this is coming to A input, this is coming to B input, and both are getting processed and going to G input. So indirectly saying that two clocks are feeding to one input. Okay, this is not correct. Okay, so I mean logically what happens is how you control is D1 should be 0. Even my clock is high, you will obviously get 0 value here. So this clock will not be driven. You can enable the D2 high and clock 2. So only one clock will go output. Being this is a OR gate, so one clock will go. So this scenario is comes in a situation where you have two different clocks driving the same logic. But this in practicality, this kind of differential clock scenario you will not face. This is a design kind of issue, and we will inform the RTL team to maintain synchronicity across the entire design by having a same type of clock gating cell environment. And this kind of scenario is there. Even DFT engineers can fix it, or you can ask RTL team to fix it. So how DFT fix we will discuss later. Okay. So this is one type of clock DRC. Latches not transparent that we will discuss later. Black boxes, I think I have already told you. If black box are driving any kind of logic, if one black box, one more black box, if this is driving this, then will not have any value coming out of this output of this. So black box is there is no logic. You know only input and output pins. So if this kind of black box you're reading, but you don't know the output of the value, you'll always get X value to output of black box. So you cannot observe X value. That means you make this as a uncontrollable, unobservable. Similarly, same going as input, X is going as input. That means you cannot control this. So any X propagation for input or output, it is unobservable or uncontrollable. So these all come into test 451 DRC. Okay. These are test DRCs. Apart from D naming convention, this will be like this test 451, 421, different type of. Yeah, these are the full forms. I think DRCs is done. We are done with DRCs. Full forms. Before going to DRC debug, let's see the DRC. I mean, different naming conventions and the meanings of it. ATPC means automatic test pattern generation. Okay. ATE, automatic test equipment. Industrial equipment used to test semiconductor devices by applying input stimuli, observing the device response, and comparing it against the expected response. Built-in self-test. BEAST. Built-in self-test. So we'll discuss this later during MBIST. BSD, boundary scan design. The IEEE 1149.1 is a standard which will have this boundary scan design. We already discussed it. Burn-in mode. So a mode that continuously runs autonomous self-test. So this is a stress test. Burn-in mode means you are trying to pressure the IC with a continuous toggling. So you are doing a stress test, okay, which will give you which will check the power fluctuation and how it can withstand or not. Okay, so that particular design or logic can withstand this burn-in test or not. What is the peak power? At which pattern you have this peak power? At which logic in entire design? Where you are consuming lot of power? You are using continuous testing. So burn-in mode will have a continuous sequence: 1010101111101010 or 0000011111. That kind of continuous one test sequence will be there. That is meant for stress test. So that kind of test is called burn-in mode. We don't do it until unless required. CDR means core data register, part of this IEEE 1500 implementation. Clock chain is a chain, scan chain that you design I mean clock chain, right? It's a OCC controller. You have a shift register, right? In OCC, that is a clock chain. You stitch that. That is clock chain. Clock gating, we already discussed what is clock gating. Codec is a compression technique of synopsis. So codec means uh, it's a compression technique with decompressor compressor. We did not discuss this yet. There is a second chapter we will discuss in our DFT curriculum. So all this you can understand later. Let's go into TRC checks. How to debug, okay? Okay, this is from my company, I mean my previous company. So D rules that take DFT compiler, for example, normally we will meet many DRC rules when we do pre-DRC checks. Some of the DRC rules will stop scan insertion that we have already seen. Some of the derule violations prevent violated cells from stitching into scan chains. Obviously, these D rules, certain D rules, will stop this particular violated cells, the cells that are violated in the form of DRCs, will not be stitched in the scan chain because they are practically not scannable because of the DRC violation on that. And other violations might just be informational or simply provide a heads up for potential impact on downstream ATPG runs, like the fault coverage DRC that we see. So all these are additional violations. Okay. Next thing, DFF clock input not controlled. So these are all the synopsis DRC table starting from D1 to D39. Okay, which are commonly seen and observed and which you have to mandatorily fix, that you see this impact based on impact. Exclude cells from scan. If something this kind of DRC is there, that is mandatorily you have to fix it, no matter what. Otherwise, you're not stitching that particular flop into scan cell in the scan chain. So your test coverage or fault coverage might reduce, because our ultimate goal is to have a good test coverage, okay, and fault coverage. So this is mandatory to fix. Any violation that is excluding cells from scan has to be fixed. This is a statement for pre-DFT DRC. Remember that. Now, D1 to D6 all are related to clocks and set and reset. Now, first DRC is DFF clock input not control. So let's see how we fix these DRCs. Okay. Actually, this presentation was prepared by me for teaching to our internal team 4 years back. So hope this is helpful for you guys to understand. Okay. So when you have DRC D1 violation, first thing is that D1 violation you will get when your clock input is not controllable. Clock input is not controllable means either you did not define the clock, or even after you define, you are not able to toggle the clock. Either it is constrained to 0 or 1. Only these two violations will be the issue. Okay, let's see that. And this, along with these two, this clock might be coming from a ICG, integrated clock gating cell. So even if clock gating cell test enable pin is not, the test enable pin is not active, then also clock will not propagate. So we'll see how to fix them. Okay. This is clock. This is the clock. This is a logic, and this is a clock gating cell. After a scan clock or a functional clock, whatever the clock, assuming in DFT it is a scan clock. For scan clock, there is a clock gating cell, and test enable pin is active low. When test enable pin is active low, clock will not propagate. So here there will be an OR gate, right? OR gate with functional enable and test enable. Are you guys able to understand this concept? You're able to follow up, right? Yeah.
Yes, sir.
Now this particular scan clock, okay, like every clock in the design will have a clock gating cell, either by the RTL team or during DFT insertion. So if you have a clock gating cell for this particular functional clock or a scan clock, then make sure the test enable of this clock gating cell is active and controlled by your scan enable signal. So if you don't have this, then you have to add a test point. Okay. So what is the test point here? What type of test point you are adding? You are adding an OR gate, additional OR gate on the test enable pin with scan enable, and the other input is also tied to this scan enable. When same input is being driven to the both the inputs of a combination logic gate, you might end up with a contention. But to avoid contention, we will add a buffer that will behave as a delay as well as the driving element. Okay. So buffer has many advantages. So scan enable, you give it. So indirectly, both the inputs are controlled by scan enable, and you are giving it to test enable. So this is the additional logic that you add to fix the D1 violation when you have this kind of scenario. If not, if you don't have any this kind of scenario, clock gating cell, make sure that your scan clock is defined as a add clock through add clock command in the protocol, test protocol. Is this clear?
Yes, sir.
Okay, next. Again, one more scenario is, if you don't want to fix this particular thing, you can directly fix this. And again, even if you fix it, I think there is some additional combination logic here. Okay, you don't know what could be the output of this combination logic, because the combination of input might not just be from this particular clock gating cell. It might be from some other combination logic gate coming into this particular again another combination logic and driving to the CP. So even if you fix this particular thing, you might get an X value going into CP. In such scenarios, your main priority is that every clock pin has to be controllable. That is the agenda of DFT. So we will add a mux with a select line of scan mode bypassing this. So if you fix this one, the fixed clock output will come, clock gating cell output of clock gating cell, and it will directly go as to the other input, and it will be controlled by scan mode. So we can we can only just fix this, or we have to do both. If that is a question, then we have to fix the both, because of one scenario that whatever you do in DFT, do not change the functionality of the design. Got it? Whatever you do in DFT, never change the functionality of the design. Okay. So if you're change the functionality of the design, then you have to make sure that it is updated to the RTL team. And by default, you should never change the design. Now, you have made changes to this test enable pin. Test enable pin is purely dedicated for DFT. Okay. So you have added scan enable logic. So scan enable when is high, then only DFT test enable pin will be active. When scan enable is low, obviously again it is going 0, the original behavior. Correct? This part is
Right.
understood? Right.
Yes, sir.
And when you are enabling scan enable high, and this output has to reach to this particular CP without any barrier of any intermediate combination logic that might give you a chance of producing X propagation output. You bypass this path and make a mux here. Okay, this is a way of fixing scan DRC when you fix it manually. This kind of fixes are manual fixes. Okay, this fix is a manual fix. Manual fix means you have to write a script for all these connections. Okay, and you have to fix it and you have to rerun the DFT compiler, the tool. Okay, can I go to the next DRC?
Yes.
Next, D2, D3. D2 means set violation, D3 means reset violation. So every flop will have set and reset. So you need to have control on both set and reset. So if you do not have, then you have to bring controllability. So how do we do that? No. So there are some key points. Please first check the reset of violated flip-flop is connected to the reset port, which we do not define it as a scan reset. Okay. The functional resets, are we defining them or we are not defining them? Okay. If we define the scan reset signal, it will also create D10 violation. Okay. So we will insert mux on the internal pin instead of directly defining the scan reset pin. So instead of defining a reset signal, we will add a mux, which will help out in bypassing any or creating any additional violations. Okay, so the basic point is that inserting the mux will not cause many D10 violations, and if you have D10 violations, you will have a coverage loss. So whatever you fix in scan insertion, the DRC fix, make sure that you are not disturbing. I mean that DRC fix is not impacting on the scan coverage later stage on the ATPG side. Okay. These points are clear. Okay. So if you see here the scenario, this is the DRC. So you see that scan reset, okay, pin is going, but you have a combination logic in between, and then it is going to the flip-flop. Similarly, this flip-flop output is driving to some combination logic gate and then going to this flip-flop. Same here. So if you fix the issue for this output of this combination logic gate at this point, it will fix for this as well as this. And here, if you fix, it will only fix this particular DRC. So you need two fixes here. Okay. As long as you are getting a proper value output of this combination logic, either 0 or 1, a concrete proper value. Okay. As long as you're getting that, you don't need to add any control or a fix for this particular path. If you are getting a proper value, you don't need to get fix here. Until unless you get a X propagation value coming out of any combination logic that is driving to clock or resets, you need to add fixes out of this X propagation. Is that clear?
Yes.
Right. So again, the same fix. What we are trying to do is add a mux, I0, leave it as to be because it's a functional path. We don't want to disturb. Add mux to the scan 1, I1 of the scan mux, feed it to the original direct port of scan reset, and control signal is scan mode. So this is how you do fixing the scan reset violation. So D2 or D3, any violation with this fix will be resolved. Any question here?
No, sir.
Okay. Is it clear to everyone? Can I move further? Okay. So D8 violation. So D8 violation is something, see, like this: scan clock or scan reset, or just clock or reset is driving indirectly to the D input value, and the same scan clock is directly driving to the same clock input. Okay. So clock not able to capture violation. So the port we define it as scan clock or scan reset, but it does not connect to the clock or reset pin of flip flop directly. It is connecting to the D input. We should not define it as a scan clock or a scan reset. Make sure that if something in this kind of scenario you have, you just don't define this particular scan clock or reset that is coming as input to the D input. Don't define it. That is the resolution for this. Okay. So these scenarios you will see in a situation where in this previous company that I worked, uh, we used to manually create scan clock and scan reset during scan insertion, and not use, and we never used the functional clocks or functional resets. We always created new scan clock and reset for our DFT purpose. So in that scenario, right, you already fixed all the DRCs so far for a D1 and D2, and next you came to D8. So whatever you fixed in D1 and D2 with scan clock or reset, that is creating this D8 violation, because actually there is a functional reset or a functional clock that is already driving this D input. So you just don't define that as a scan clock or a scan reset uh, in the scan instruction script. Just use the created scan clock or reset. Okay. So if you're confused, let me just say it clearly again. So in my design, existing design for that particular partition or a block, I have func underscore clk, func underscore reset, that is originally going into the flip flops clock and reset respectively, either through ICGs or resets or anywhere. Okay. So next thing is I have created scan clock and a scan reset. In my flow, I don't want to use function clock or function reset. I don't want to disturb these paths. I'm creating muxes and adding new ports purely for scan clock, purely for DFT purpose. I'm creating two new ports, and I'm using this. So when you are using only these, make sure you are not defining any of these two things as a during test protocol, in the test protocol, in the name of scan clock or reset, in the pre-DFT or existing DFT signals. So if you define, both will be shown, both are active. So that will be a problem. Either one should be active. Okay. In DFT, either any one, only one should be active, either scan clock or func clock. Okay. Purely for shifting purpose. Okay. During scan insertion, I'm telling. So this is understood.
Yes.
D8 fixes. Make sure don't define any functional clocks or resets. So any DRC that you're getting, automatically tool will show that a certain clock that is this is so and so clock is not able to capture violation. Then you don't define that as a clock. Only when you have D8 violation. That is for D. That is a fix for D8. So whatever we discuss in this are the major DRCs that you will face across in your DFT career. Mostly these are the DRCs. 99.9%. These are the DRCs you will face. That is the reason these are the highlighted and explained the debug solution for that. D9 violation. So clock port not active when clock set to on violation. So clock port is not active. The clock input CP of the clock input name is CP of D flip flop DFF, and the DFF is the path. This is the path of the D flip flop, not active when clocks are set on. Okay. So first what we need to do is we have to check if this clock pin is driven properly. So the majority of the times DI9 is something your clock path is not controllable. Either it is stuck at 0 or you have clock gating cells in between. Okay. If you have clock gating cells in the path of CP, or you have clock gating path directly tied low, you will face this issue. Okay. So if the clock pin of flip flops is undriven like this, you have to inform to the front end team. Okay. So PL means project lead. So you have to inform to the DFT lead, and DFT lead will update to the RTL team. It's a functional issue. CP of the any flip flop should never be tied low. Clear? Okay. And there is one more scenario which is not captured in this particular presentation. One more scenario of D9 is recently I have fixed in the current project that I'm handling in Intel. What is the scenario? Clock gating cell D9 violation. We're getting D9 violation because of yes, because of there is a clock gating cell in between, and the clock gating clock gating cell and clock gating before the clock gating cell there is a mux. That mux select line is not defined. Okay, that means there is a clock gating on this clock path. Before the clock gating path there is a mux, and that mux select line is not controllable. So that means not defined as an existing DFT signal. So that the clock, I mean that mux select line is X, then the mux output will be X. That is causing the D9 violation. So do not always stick to one type of DRC violation. That means there could be various ways you end up having the same DRC in real time. So in one project you might have one kind of scenario that is causing D9. In another project it might be different, or block to block also within same SOC design, partition to partition you will have different D9 violations. Okay, if it is same, luckily majority 80% of the time it will be same. 20% it might not match. You might have a different kind of D9 violation. Okay, can I move forward? This is issue is understood, D9 and its fix.
Yes, sir.
Next, D10 violation. So D10 violation is clock feeding data input violation. That previously in discussing about the DRCs we came across this, right? So scan clock or reset going into D flip flop. I mean going into combination logic, and combination logic is going as a feeding to D input. So this is very danger. D10 has to be fixed. So these DRCs are mainly because you have fixed the D2, D3. By default, you will not have any D10 violation. The D10 might be caused due to fixing of D1, D2, D3, D9. It could be possible of from any of these above DRCs. So there is also a golden rule for a DFT. Make sure any DRC that you're fixing should not create one more DRC, okay, or a different DRC. So you should be aware of this concept of all the DRCs. So when you're fixing one DRC, you should think, you have to forecast whether, okay, if I'm fixing something here, is it will it cause any other violation, particularly D10 violation. Most of the time, D10 is the one DRC that you will get if you fix any D1, D2, D3, D9. So D8 and D10 are caused by the fixing the existing D1, D2, D3 violations. Okay, so D8 and D10 are the additional DRCs that you get because of fixing the existing DRCs. Now, how do you fix it? The clock of newly added flip-flop should be the same with the clock of violated flip-flop. So, the fix is you add a mux with a flop in the below fashion. Okay, in the below fashion. Okay, add a flop here. And the scan clock should go to the added new flop. And the D input, the Q, should be always in a loop going into I1. Okay, and the the I0 should be the select line should be scan mode, and I0 should be the scan clock or reset. So what happens now? Now execute the operation. You are want to do shifting. During shift, scan mode is high. Okay, when scan mode is high, scan clock is high, the D value, the value in the D flip flop, that particular flip flop, okay, is coming in as input and going into the D. So the flop output is coming into the combination logic and then going to D flip flop. This is not this isn't any DRC violation. This is not violating any design rule checks. If a clock is directly driving into D input like this, then it's an issue. What we are doing here, we are trying to bypass this particular input. That's what we are trying to do here. If you want to bypass anything, and if you want to give you a proper value coming out of flip flop, then you have to add a flip flop followed by a mux with a select line of scan mode. This kind of logic will fix the D10 violation. In the previous company, 3 years back, oh god, D10 violations used to be in thousands, 20, 40, 60, 80, up to 90K. Also, I have seen D10 violations. You have to fix like this. It was horrible because you get all these kind of dumb DRC issues when you are creating separate scan clock and separate scan reset instead of using existing function clocks. Okay, so the flow was like that. We cannot do much. So not every company will have a similar flow. Company to company, the flow will be changed. So as long as you're, I mean, you are not technically that good after working for 1 or 2 years in some company, don't change a company until you are technically good. Okay, not just package is low or you want to suddenly get a good package. Okay, so don't go in such a way. You will end up having problems that when you have 3 years of experience or 5 years of experience, there will be some expectations from you, from the lead or a manager, because you have some 3 years or 5 years experience. You're an experienced engineer, so they will expect some technical stuff from you, and if you don't perform it, so you will not see much hikes or much growth going forward. Okay, so first 3 years you should work hard to understand each and every concept very clearly, and uh, you have to contribute the same by in the form of fixing the DRCs or communicating within the meetings, team meetings, and all. How much technical knowledge you want to showcase, you can show, which will create good impression to the leads and managers. See, unlike software, in semiconductor, definitely you have to showcase your technical skills. This will not be like a show off. You have to show. Purely, we are in a technical genre. Semiconductor is purely technical playground. So, if you have a good skill set, you have to show it. Okay. If you don't show it, nobody will know. Nobody will know that you have that skill until you show. Nobody will doesn't know that you have skill. So even in software also, this is the same scenario where if you have skill set, you have to showcase. Then only you will grow very faster than others. Okay. So it's all a competition everywhere where you have to showcase your skills and excel. So there is one more scenario for the same D10. So if the above scenario you have, this kind of scenario you have for D10, where scan clock is going into one flop and the same scan clock is going to another flop, but this particular source flop output is going feeding into the combination logic, and that output is going to D input or a scan input. I think this is scan input or something. Mm, either input, scan D input or a scan input. Fix is same. You already have a flop, so no need to worry. Okay, the value going into D flip flop should not be directly from a clock port or a reset port. If it is from a flip flop, a proper register, then it is accepted. D value should not come from a clock port or reset port. So that is why we are fixing it by adding a mux. We are bypassing the existing path, adding mux, giving this output to this D, and adding a scan mode. So when scan mode is high, then only the behavior will be like this. If not, during functional mode, that means when scan mode is 0, the functional behavior will be as original. Okay. I think, what is the time there?
12:30, sir.
12:30. I think we shall go for a break. Okay. Are you guys okay for the afternoon session, or how do you want the session? You want afternoon session or directly on Monday? We have enough time. We are taking day every day. We are taking sessions, so we have good enough time. So no rush, no hurry. If you want session in the afternoon, we'll have it. Otherwise, you can have it on Monday.